Okay, welcome to the lecture here. We're going to continue on in chapter 13, Equilibrium. And a reminder today, like I mentioned a couple of times and sent out the announcement, we will have lecture like normal, and then the quiz will happen at the beginning of lab. So we'll talk more about that towards the end here of lecture. Okay, so we got into chapter 13, and in chapter 13, we're talking about equilibrium and chemical equilibrium. And chemical equilibrium, a reminder, as we really talked about, does involve a certain type of reaction, and that's a reversible reaction to take place. And that reversible reaction basically means that we do have basically two directions happening, a forward direction and a reverse direction. And what it means when we do reach equilibrium or chemical equilibrium, like we talked about last time, is again, not that you have the same amount on both sides. So you don't have the same amount of reactants and products or anything like that necessarily. What it really refers to is actually the rate. And it's the rate of that forward reaction is going to be equal to the rate of the reverse reaction. And that's what we mean when we do reach chemical equilibrium. Again, the rate of that forward one will equal the rate of the reverse one. So just as quickly as it sort of forms products, those products will recombine and kind of head the other way and kind of make back your reactants. So because you have a rate that's equal to each other heading in both directions, what ends up happening when we actually do reach equilibrium is wherever everybody is in terms of their concentration, their pressures, whatever it may be, they sort of lock themselves into place. So they're sort of locked into that. Unless you do something to kind of mess up the equilibrium, they'll be able to maintain that equilibrium. And we could kind of see that in this graph here that I scribbled on, I think, at the end last time. This is our N2 plus our H2, making our NH3. And like we would probably assume in a lot of reactions, once it begins, we pretty much only have reactants. So as you can see here, at the beginning of this reaction, this is a reactant, this is a reactant, and here on the bottom, we have pretty much nothing in terms of products. And in order for products to be made, really what's going to happen is that forward reaction, like I was talking about last time, essentially will start and will really kick off that forward reaction will have to take place. So sort of at the beginning of this, the forward reaction will sort of predominate. And as the forward reaction starts to go, we're obviously going to see a decrease in the concentration of our reactants. In the same time, we should start to see an increase in the concentration of our products, which is what we do see if we look at the bottom line here. As the reaction starts to go, we do start to see an increase happening in the amount of products being formed in this particular reaction. And this process will continue. And at some point, you'll get enough products that the reverse reaction will actually start to take place. And when the reverse reaction starts to take place, then we will now have it going basically in both directions. And at some point, that you will hit that part where the rate of the forward direction will equal the rate of the reverse direction. And that is where chemical equilibrium has basically been reached. And we can see that in a graph, even though I kind of scribbled over it really bad here. But if you remember kind of what these lines look like before, they were pretty much plateauing out there. So they all kind of leveled off and remained constant. And that is the point where chemical equilibrium has been reached, where those guys basically will remain constant, because they will basically mean that in order for them to remain constant, the rate of the forward and reverse reaction has to equal each other. And that's, again, how you know you sort of hit chemical equilibrium. Again, this is a nice little illustration as well. You can see that as we've been talking about, chemical equilibrium does not mean that you have the same amount of everybody on each side. You can see we obviously have different concentrations of the H2 and H3, or N2 in this particular case. But what you can see is at some point, those concentrations sort of lock themselves into place, and they're able to really maintain their concentrations once that chemical equilibrium has been reached. Any questions on that so far? Okay. Oops. So if we look at another sort of reversible reaction here, again, initially we could assume that we don't have any products happening here, no H2 or CO2 in this particular case. And we mainly have just our reactants, the H2O and the CO. And as the forward reaction starts to go, again, we would start to expect, like we saw in the previous graph, the concentration of these guys go down, while the concentrations, again, of these guys will start to rise. And again, it will continue to do that until the rates are equal to each other, and they reach basically chemical equilibrium in that particular case. And that's graphically sort of how you can determine it when you're looking at sort of concentration versus time, or reaction rates at some point, basically reaction rates versus time here. Again, they're going to equal each other right about there, and that is when equilibrium is reached. That's the same point in the graph where we saw everybody's line sort of plateau out and chemical equilibrium has been reached. Now, if we look at a reaction such as this one that we were just talking about, the H2O and the CO, and the H2 and the CO2, if we added more water to the flask, so if we have this system that has reached equilibrium, and if we decide we want to add more water to this particular situation, the flask, we want to think about what would happen to, say, the concentrations of everybody when we do that. So for example, here, if we added water, let's start with the CO. So in this case, if we added some water, which is this guy, so we added some of this, the concentration of CO we would expect to go down. And that is because when we start this reaction, or when we have this reaction at equilibrium and we add more water, what that's essentially going to do is provide more waters available to react with CO, and that's going to really initiate the forward reaction to take place. So that's going to initiate that forward reaction to really take place when you add that water. Again, availability of reactants to react with each other, going to really make that forward reaction happening. So if that forward reaction happens, that means that we do need to use up some of the CO, right, to make our products. And we would also then pretty safely assume that the concentration of the H2 should start to go up, and the concentration of the CO2 should also go up, again, because we're really kicking off that forward reaction taking place. Now, H2O is an interesting answer for a question like this: what might happen to the H2O? And the reason that is because you literally opened the flask and dumped some more water in there, or added some more steam, I guess, to it in this particular case. And what will actually happen to the water is the water will actually go up first. And the water will go up because you artificially added water to it. So the concentration is definitely going to go up. But once you've added it, it is going to start to react with the CO. And what you should see is it then should start to work its way back down. And again, you get this sort of artificial increase in the water because you added it. And then you should relatively start to see it come back down. And because you actually added the water in this particular case, you may actually see it end when it reaches equilibrium again, perhaps actually higher than it started with. And that's only because you artificially added it. So it artificially bumped up, and then it started to come back down as the forward reaction sort of took place. Any questions on that there? So if we take this same sort of idea here and we have this same system at equilibrium, but instead of the water added, if we decide let's add some H2 to this flask. So if we decided to add a little bit of this guy to it, how is that going to sort of affect everybody else's concentration? So take a moment and sort of think about what's going to happen to everybody here, and then we'll talk about it. Okay, so if we add H2, kind of the same idea, we're actually adding a product here. And by having the availability of H2 there and a little bit higher of a concentration, it's going to really initiate that reaction between our two products. And what that's going to do in this particular reaction is actually sort of kick off the reverse reaction to take place. So that will sort of kick off the reverse reaction in this case, which means, again, in order to make our reactants, which are kind of like our products, head in the reverse array, we will need to use up some of our CO2 to do that. And we would expect the CO2 concentration to start to decrease. Now, because this reverse reaction is kicking off, we then should be making more reactants in this case, and we should expect these guys' concentrations basically to increase. And the H2 here will be very similar effect that we were just talking about with our H2O. Again, at first, we definitely will see it increase. And again, we do see an increase in the H2 because literally you opened the flask and you added more to it. So you literally added it. But once again, that reverse reaction really kicks off, we will start to see the H2 being used as well to make our reactants. And we will again start to see it come back down. So again, for the thing that you added, you oftentimes will see this sort of artificial increase because you added it, but then you'll see the general trend you would expect would be it will come back down. Again, may actually end up higher than where it started, and that's just because you artificially sort of added it to it.
But then the H2O and CO will increase, right?
Say it one more time. The H2O and the CO will increase. Is that a yes?
Yeah. Is that what's gonna happen?
Yeah, it's going to happen because once you add the H2 to this mixture that's already at equilibrium, it's going to initiate that reverse reaction. And in the reverse reaction, basically these guys here become like our products that are going to be made. And so the reaction is going to head to the left. And when it heads to the left, you should expect the concentrations of H2O and CO to increase, while CO2 will decrease because you need it to react with it. Other questions? Okay. All right. That graph again, in case you missed it the third time. let's actually talk about the equilibrium constant and its application. So the equilibrium constant is a relationship that you can write for a reaction that's reversible and a reaction that reaches equilibrium. And the equilibrium constant is capital K. Again, not lowercase k, which is our rate constant from the previous chapter, but it is capital K, which stands for the equilibrium constant. And that is something that you should get used to because that's pretty much all we talk about here for the next several chapters is capital K, which is our equilibrium constant. So if we have this reaction here, or this equation, we could write capital K, and it's equal to the concentration of NO2 squared divided by the concentration of N2O4. Again, a reminder that when we do see the little brackets, that means concentration. And that typically is molarity, which is moles per liter. And the way we do this is basically the equilibrium constant is the concentration of the products divided by the concentration of the reactants. And what we do here in equilibrium is we actually do take the coefficients as the exponent. So that's where the squared part comes from, the 2. And the coefficient here is obviously a 1. And that's why obviously this is to the 1 in this particular case. So we take the products over to reactants and it gives us a number. The number for this particular one, not important for anything here, but it was 4.63 times 10 to the minus 3. We'll talk about what that sort of means in just a second. But in general, when you go to write an equilibrium constant expression, It is always the concentration of our products over our reactants. And we do use, so a little bit different than kinetics here, we do use the coefficients as the exponents. So this relationship of the concentration of products to reactants is constant. So that's why it's called an equilibrium constant, which means for a particular reaction at a specific temperature, the equilibrium value will be the same at the same temperature for a reaction. So as long as you keep the temperature the same, you could start with as much as you want of the reactants. You could start as much as you want with the products. It does not really matter. It will always come to rest at equilibrium with the same proportion of products to reactants. So that is something as well that sometimes people have a little trouble with the equilibrium idea, is if you start with different amounts of, say, reactants and you throw it in there, it will always come to equilibrium with that same proportion of products over reactants, which is known as the equilibrium constant. And sometimes people think, well, how could that be if I started with, say, 40 this time, but I only threw 3 in there the next time, and say to start with. And it has to do with, again, that point where the rates of those guys equal each other, whatever the numbers are on each side of products and reactants, those ratios will always end up being the same. And that's why, again, it's equilibrium constant. And really the only thing that will affect the actual value of K, as we'll talk about in this chapter, the only thing that really affects the value is temperature. So if you keep your reaction at, say, 25 degrees Celsius, and you do it a ton of times, the same reaction, again, starting with different amounts, it should always end up with the same K value. But if you take it from 25 degrees and change it to 60 degrees, the value of K will be different than it is at 25 degrees. But once you get to 60 degrees Celsius and keep it there, it will remain the same, all the equilibrium values. So temperature is really the only effect that will change the actual value of the equilibrium constant, but it will remain constant at a specific temperature. And as we'll talk about in this chapter, when you do see an equilibrium value given, it is also specific for exactly how the reaction or equation is written. So here, as you can see on this generic equation here, we take our products over our reactants. Again, our coefficients become our exponents on both sides. And again, this will give you a number. And the nice thing about the equilibrium constant as well is it is just a number. So there's no units typically associated with the equilibrium constant. It is actually just a value or a number. And what does that number perhaps tell you? And the number does tell you certain things. If you have a large value of K, what that means, if you just think about it mathematically, if you have a large value of K, when you reach equilibrium, you would have more products. Just mathematically speaking, if you take a large number on top, which is the products, divided by a small number on the bottom, which is reactants, that should give you a large number. And that's what the value of K will tell you. If you have a large value of K, you mainly have products when equilibrium is reached. And if you have a small value of K, it's basically the opposite there. And a small value of K, that means that you would have a larger number on the bottom, smaller number up on top. So small number divided by large number means you have a small number, and you'll end up with mainly reactants when you reach equilibrium. So the actual equilibrium constant does tell us these things. It does give us a indication as to when we do reach equilibrium, you know, what would we expect to be there? Would we expect mainly products to be present? Would we expect mainly reactants to be present? So you may ask yourself, you know, what is a large value versus a small value? And a large value is that big number of 1. So anything above 1, as you can see here on this slide, is considered a large value for the equilibrium constant. And again, what that means is we would expect more products there than reactants. And that would mean that we would favor really product formation when we have a large value of K. Opposite is true if you got an equilibrium constant that's less than 1. So something with a negative exponent, we would expect the equilibrium to lie to the left or to favor the reactants. Again, small number divided by large number gives us a small number in that particular case. So the actual number is important in the sense of if it's greater than 1, you could assume probably should have products there. It doesn't mean you have no reactants. It just means that you'll have more products than reactants. And if you have a smaller value of 1, again, it means you should have more reactants than necessarily products in that particular case. Any questions on that there? So just to illustrate sort of that, if we look at Mickey Mouse there, plus a couple other circles, makes Mickey up on his head on the other side. And if we have a K value here of 25, would we expect more reactants or products when we reach equilibrium? So take a second and think about what you think the answer is. And when we would look at this here, we do see that the equilibrium constant is 25. That is definitely above 1. So we would think that we would favor products here. Again, the idea is basically it is the products divided by the reactants. So in order to get a large number, we got to have a bigger number up on top, which means we should favor the products being formed. Any questions on that particular one there? Okay, so let's talk about actual sort of equilibrium and different types of equilibrium. First type is homogeneous equilibrium. Homogeneous, much like a homogeneous mixture, means the same throughout. When we talk about a homogeneous equilibrium, that means everybody there, reactants and products, are all in the same phase. So for example, here, everybody is in the gas phase. And we could write an equilibrium expression for this like we talked about. K is equal to the concentration squared of NO2 divided by the concentration N2O4. But since these are actually gases, when we think about gases, we do think about pressure, right, as well. Our good friend P equals nRT. So we could think about pressure. And sometimes when we're dealing with gases, we may be following the actual pressure change. So we could actually write an equilibrium expression that deals with pressure. And it's the same thing. It is the products over the reactants, except that here we are using partial pressures. So this is the partial pressure squared of NO2, which is our products. Again, the 2 here still comes from the coefficient. Divided by the partial pressure of N2O4, which is our reactant. And again, coefficient here is 1, so that's why there's nothing up here. And these two K values or expressions are sometimes also separated. This guy over here is sometimes what is referred to as the Kc value. So that is our very first equilibrium sort of expression, Kc. We will add it to a ton of different K values throughout the semester. So Kc, creatively C for concentration. So we're doing our concentration of NO2 squared over the concentration of N2O4. This is what is known as the Kp, and I imagine you could probably figure out what the P stands for, but P for pressure here. And this is our partial pressures of NO2 over N2O4. They are both the same. They're both ultimately equilibrium expressions. They are both really just going to end up being a number with no units associated with it. but they do tell you kind of the same information. Although in most cases, they do not numerically equal the same value. They do give you the same type of information. So much like a KC, if you have a large value for KC, means mainly you have products. If you have a large value for KP, it also means you mainly have products, and probably on that product side, you have a gas that's contributing a lot to the pressure. And vice versa, if you have small values, reactants, and you would have reactants mainly that are providing the pressure. So in certain cases, you may need to calculate the KC and you only have information about KP, or pressures, and vice versa. Maybe you need to calculate the KP and you only have concentrations. So there is a way that we can go between those two, and that is using this equation here. The KP equals the KC RT delta N. So let's talk about what some of these guys are here in this formula, and it's in a box, so I'm assuming you do need to know it. So KP, KC, RT, and delta N. This is our equilibrium constant for pressure. This is our equilibrium constant for concentration. This is our gas constant, and this is actually the gas constant that you use in the ideal gas law. So it's the same R that you would use in here. That is 0.08206. R if you use more of the rounded version of it, either one. And again, the temperature here, much like a gas sort of thing, does need to be in Kelvin. So R is the 0.08206 version of the gas constant, the one that you typically use in the ideal gas law. T is our temperature, which is Kelvin, like you usually do in gas laws. And delta N is the change in the moles of gas products minus gas reactants. So it is products minus reactants, and N, just like in the gas law, is moles, and that's a change in the number of moles. And it is important that you do that calculation correctly. So for example, let's say we had a particular equation where it was, let's do 3A, that's all gases, goes to 2B, that's a gas. Now, if you go, all right, the difference between these two guys is 1, because you took 3 minus 2 and just did the difference. Or if you did it correctly and found that delta N would be our products, which is 2 minus our reactants, which is 3 gas molecules, minus 1. Now you may say to yourself, doesn't seem like there's a big difference between those two numbers, but mathematically there is a difference with that negative, because when you go into here and you take a number to the 1 versus a number to the -1, mathematically speaking, you're doing a different operation there, and you will get a different number. So really important to make sure that you actually do it correctly and do products minus reactants, just the gas molecules involved there, and make sure that if you do have a negative on that difference, that you do take that into account. Again, mathematically, it would be very different, sort of the answer that you would get. A same thing, for example, the difference was 2 versus -2, right? The minus means you're basically taking 1 over it squared, right? And without the minus, you're just squaring it. So again, you will get something different mathematically. So really important not to just take the difference in the gas molecules, but again, incorporate obviously the negative part of that correctly based on what you got there. All right. Any questions on that? So KP, KC, 2 different equilibrium expressions. One deals with more concentrations, one deals with pressures, and that nice guy in the box there is a nice way you could go between them to calculate. And it is going to be based on the information given to you most likely. So again, if you're given concentrations, you've got everything you need for KC. If you're given just pressures, then obviously, you know, you got to go KP first and then convert it over using that equation. So when we look at a homogeneous equilibrium such as this is acetic acid plus some water, make some acetate and some hydronium ion. If we write our equilibrium expression like we normally would do, we would take our products over our reactants. And in a reaction, and when you write an equilibrium sort of expression, something like water, for example, its concentration remains constant. And what that means is if we were to write the equilibrium expression for this particular reaction, we would not include the water. So the correct sort of equilibrium expression for this particular reaction is our products over the reactants, but we don't really include the water. And the reason we don't include the water is it is actually a pure liquid. So anything that is really a liquid, and we'll talk about it in just a second as well, are a solid, does not get included. In the K expression. And again, that's because they essentially remain constant as these reactions take place. Their concentrations really don't change all that much. So it basically just stays the same. So if you think about even solutions that are aqueous, that all has water in it. So extra water, a lot of water in there. So very hard to sort of change the concentration of that water. So in general, if you're writing an equilibrium expression, we again do not include anything that is a solid or a liquid in it. And that really does leave us only two things when we write K values, and that is anything that has the aqueous symbol or anything with the gas symbol next to it. They do get included. So essentially those two guys, if you're looking at an equation, you see those two guys, those guys should be included. If you look at an equation, as we'll see here with the liquid, we really don't include it. And if we have anything later on, as we'll talk about with the solid, we don't include that either. And as I mentioned before, we essentially do not use units with the equilibrium constant. And really, occasionally you'll see some people leave the units in, but they really don't cancel out very nicely and stuff like that. So sometimes you're left with weird units. So pretty much nobody uses units with the equilibrium constant. I have seen it a few times and some people have left them, but you usually shouldn't use any units or anything like that. So just a number, no units. And again, the importance of that number is it will allow you to determine, what's going to happen when you do reach equilibrium. Do you have products? Do you have reactants sort of present mainly? So I want you to take a moment here and write the KC and KP if possible for each of these, and we'll talk about it and see what you come up with. Okay, so let's take a look here. So looking at the first one here, A. We're going to do our Kc, which is going to be the concentration of our products. So that's going to be NO2, and we are going to take it to the fourth power because of the coefficient. We're going to times it by O2, which technically is the first power because coefficient is 1. We're then going to divide it by our reactant. So that is going to be N2O5. We're going to square it because of the 2. And that's all I got on the reactant side. So that would be it. So that would be our Kc expression. Since they're all gases here, we can write a Kp. And it would work just the same way. The only difference is here we would be looking at partial pressure to the fourth of NO2 times the partial pressure of O2 divided by the partial pressure squared of N2O5. So that's what that guy would look like. Again, looks pretty similar other than partial pressures versus concentrations. Any questions on that first one? So our Kc here, again, same idea. We're going to go products, which is going to be H3O plus F minus divided by HF. And here would not be included because it is a pure liquid. So that would be our Kc value here, our expression. And in this particular case, there are no gases. So you can't really write a Kp since Kp has to do with pressures. And if there's no gases, there's probably no pressure going on or anything like that. Any questions on how to write these expressions? Okay. So why don't we try a calculation one here? So why don't you take a couple minutes to see what you come up with. We have the equilibrium concentrations for the reaction of carbon monoxide and chlorine to form CoCl2 at 74 degrees Celsius. We have 0.012 for CO, 0.054 for Cl2, and 0.14 for our CoCl2. Calculate both the Kc value and the Kp value. So take a couple moments here, a couple of minutes, and see what you come up with, and then we'll talk about it. Hopefully we'll all be on the same page.
Oh, Professor?
Yeah.
For the last example, for B,
Mhm.
there was a Kp, right, for B?
There was not because there was no gases. So you can't have Kp because there's no gases. So no gases, then you can't really have any pressures and that type of stuff. So pressure, a good way to remember it, pressure is usually associated with gases. So you need some type of gas in there for it to be able to write one.
Okay, thanks.
You're welcome. Okay, so let's take a look, see how we're doing. So we want to find both the KC and the KP in this particular case. So really, how you're going to approach it is based on sort of what was given to you in the problem. So when we look in this particular problem, we're obviously given the equilibrium concentrations of everybody. So that would tell us that probably we should start with the KC since we do have the concentrations. So the KC expression in this case would be, again, our products divided by our reactants, CO and Cl2. And we just want to put all the numbers in the right spots here. So 0.14 up on top, 0.012 on the bottom, and 0.054 on the bottom as well. And if you do all that good stuff and you punch it in there, we end up with something on your calculator like 216 as our equilibrium constant for our KC. Now, if you want to sig figs, which since it's a chemistry class, probably should look at things like that, but all kinds of 2 sig figs. So perhaps we go to 220 on a probably better significant figure sort of answer in terms of that. So we have 220 as our KC, 216 if you kind of ignored that whole sig fig type of deal. And at this point, we do want to go to our KP. And our KP, we could use that equation or formula that will take us between the two. So we do need to figure out a couple of things here. What we want to do is delta N in this particular case. So delta N, again, is our products minus our reactants in terms of our gases. So on the product side, there is just one gas guy minus one gas guy here and one here. That is 2. So that's going to give us a -1 for our delta N. Again, the negative here is really important. Otherwise, mathematically, you are going to get a incorrect answer when you do that. So what we want to do now that we have our N, we do have the KC from above. R is a constant, so we do need to obviously convert our temperature as well. So that's going to be a 273 plus a 74, and that's going to give us a 347. So at this point, we got everything that we need. We're going to go KP. Again, 220 if you used a rounded number, 216, I suppose, if you did not. You'll get fairly close to the same number. I'm going to use the gas constant. I just use that number because that's what's in my head. Again, you could use the 0.0821 if you want. That's 347 and minus 1 here. So what we want to do is basically take 0.08206 times the 347. We want to take 1 divided by it basically and times it by our 220. And we will end up with 7.7 in this particular case. And if you didn't round, you obviously will end up with a slightly different number there. And probably would be okay, I suppose. But you should try to hit the right sig figs, obviously, when you're doing it. I think you get 7.6 if you didn't round there. Question on those calculations. Again, if we look at these guys here, you see that the equilibrium constant, again, no units. And we also see that the value of those guys is relatively large. And that would mean when we reach equilibrium, we would expect to have probably products present in this particular case. Any questions on that one there?
I didn't get 220. I got 0.063.
Yeah, so my guess is when you put it in, you probably didn't use parentheses on the bottom. So what you want to do is you probably want to go 0.14 and divide it by 0.012 and hit equals, and then divide it by 0.054 and hit equals. And again, if you try to punch it all in at once, and you don't put parentheses, you will get the number you got, I think. Alternative to that, you do need to make sure if you're going to try to punch it all in at once, that you do put the parentheses on your calculator. Otherwise, your calculator will do the different math. So if you don't put these parentheses in, if you try to do it all at once, you'll probably end up with the wrong answer. Safe way to do it on anything like this is just hit that equals button more than once. So 0.14 divided by 0.012, hit equals, and then divide it by one more time, and you should get the right answer. Other questions on that? And that does bring up a good point. You do want to watch that. It happens a lot. People always want to punch in everything all at once. And again, depending on your calculator, I'll say how sensitive it is or how it's programmed. It may not do the math you think it's doing when you punch it in like that. So usually hitting the equal sign a couple extra times usually is a safer approach, and dividing by each of the numbers by the bottom and hitting equals usually will sort of fix that problem. All right, so why don't you try another one here? I think you got. So let's see here. The equilibrium Kp is 158. What is the equilibrium pressure of O2? If the equilibrium pressures of each of those guys are given, and it is missing something there. So let's see. They both say NO, so that's not very helpful. So let's go with the 0.27 is the NO. So the 0.27 is the NO, and we'll go with this guy as the NO2. Looks like the 2 got lost there. All right, so that should be a little bit easier, I think. So give that a go. And see what you come up with. Okay, so let us take a look here and see how we're doing. So in this particular one, we're giving equilibrium pressures. So that should tell us that Kp is probably what we should look at first. So the Kp expression in this case, just like the Kc, is just going to be the partial pressure though. We're going to square it for NO because of the coefficient. It's going to be times the partial pressure of O2, coefficient there 1, divided by the partial pressure squared because of the coefficient of NO2. And in this case, that equals 158. In this particular case, we are given the NO and the NO2 pressures. So if we just kind of put those numbers in, NO was 0.27. That's going to be 0.27 squared times the partial pressure of O2 divided by the partial pressure of NO2, which is 0.4 also squared, will equal 158. We're going to bring the bottom to the other side. So what we'll end up with is 0.4 squared times 158 gets us 25.28, and that equals 0.27 squared. That's going to be 0.0729 partial pressure of O2. I'm going to divide that to the other side. That is this, by the way. And those will cancel, giving us the partial pressure of O2 of 347. And since this is a partial pressure, we do need units. So the units here would be atmospheres, as the rest of the units here were also atmospheres. So that's where the units would come from. And we do need units here. Again, we're not solving for K, but we're actually solving for a pressure. So you do need to make sure you include the units. First off, any questions on that calculation? Now, it does sort of make sense. Some of the stuff that we're seeing, we have a equilibrium constant of 158. That's a fairly large equilibrium constant, considering 1 is considered large, so 158 is pretty large. And that would mean that we would expect mainly products at equilibrium. And if we look at the pressures that are there, obviously at 347, we have a lot of O2 being generated to create that much pressure. And obviously that would make sense, since mainly we should have our products there. And the major contributor obviously to the pressure is the O2 in this particular case. Any questions on that there? It doesn't matter in this particular question. So the temperature, you actually don't need it in this question. You could use it, or I guess put it this way, now that you could have used it if you wanted to for calculating Kc. It didn't ask you to calculate Kc, but you could have used it for that. But the 1,000 really doesn't make a difference in this case. So sometimes you'll get some extra numbers in some of these problems that you don't need to actually use for anything. But if we had a second part to this question where maybe it asks you what the Kc value, then you would use it in that Kp equals Kc RT delta N. But in this particular place, you don't need the temperature. Other questions? Okay. So we sort of talked a little bit about this in just a second ago, but we do have things that are known as heterogeneous equilibrium. And heterogeneous, just like a heterogeneous mixture, means that you do see different phases there. And the same thing that happens here. For example, we have different phases going on. So here we have solid and gas in terms of the phases of everybody. And we can write an equilibrium expression. But as I mentioned kind of earlier, if something is a solid, just like the liquid, it really will not participate in an equilibrium. And the reason for that is, if you think about it, it's like you drop something solid into a beaker. It's just going to sit there and it can't really participate in anything. If you drop something that's solid and you dissolved it and it dissolved, it's no longer solid at that point, right? It's aqueous, and then it would participate. But if you just have a solid that's not going to dissolve, it's just in there, not really participating, it will have no effects. Kind of like a rock, right? You drop a rock into a beaker, you know, it's really not going to do anything other than kind of sit there. And that's sort of what you think about with solids. So we would, if we were writing the equilibrium expression for this particular one, this would actually be the correct one here. It would be not this. So just so there's no confusion, this would not be the correct one. The Kc for this would be just the concentration of CO2. And you could write a Kp for this guy because there is a gas and everything else is solid. And the Kp would be the partial pressure of CO2. So those would be the two correct equilibrium expressions for this particular reaction. Again, solids and liquids are not included in the equilibrium as they really do not participate. So this is what happens if we have, say, solid on the reactant side, but what happens if we had it sort of the other way? Let's just say we had 2A goes to B solid. So let's say we had something like this. If we were to write the K, it would be 1 over A squared. So you would do the 1 over it for this part. If this was solids or those were liquids on that side, you would not include it. You would just take 1 over really the reactants. And that's how you would write sort of the equilibrium expression. So as I mentioned earlier, solids, liquids, don't put it in. Essentially, aqueous and gases are really the only things that should be in that equilibrium expression. And here, so graphically, you can kind of see if you have your solid, you know, it's just really sitting there. It's really not participating along the way or anything like that. You know, it's just kind of sitting there, not interacting or anything like that. And it will sort of remain relatively constant, as you can kind of see. And basically the pressure associated with those gas molecules, for example, that are flying around here is not dependent on the amount of the solid that's present, again, because it's just kind of sitting there, not really participating. Also, if you had a solid that was in a test tube and it, you know, guys are floating around, it's not really floating around with it, so it can't really participate or really sort of affect the equilibrium. Although you can kind of see the amount of it can change, right? You can make more solid or less solid, but it really is not actively sort of participating in the equilibrium, and that's why we really don't include it in the expression. All right, so I want you to try this one here. We have the following reaction. We want to calculate the Kp and the Kc for this reaction, so see what you come up with. Take a moment or two, a couple minutes. Okay, so let's take a look. So same sort of approach here, since we're looking for both the KP and the KC. We want to think about which one most logically makes sense to start with. And since we're given the pressures here, KP would seem to be the most logical one here. So we'll start with our KP expression. And again, it's going to be our products over reactants here, the pressures. So it's going to be the pressure of NH3 times the pressure of H2S. And on our reactant side here, we do have a solid. So we will not include that in our expression. So that is what we got going on here. So if we put it in, we would essentially have 0.265 squared. And that will essentially give us 0.0702 as our KP value. Any questions on that calculation? Now that we do have the KP value, we could use that formula that we saw earlier, KP, KC, RT, delta N. So a couple things we need to figure out is delta N, and that is the N of the products minus the N of the reactants, just our gas molecules. So we got one gas molecule, 2 there. So it's going to be 2 minus 0 here, as that's a solid, again, not a gas. And that will give us an N of 2 in this particular case. In terms of the temperature, they were nice enough to convert that for us already. So we're good to go on our temperature. So that would give us our KP, which is 0.0702, equals our KC using our R value and our temperature. Again, we're going to square that. If we clean up the right-hand side there, 0.08206 times 295, and then square it, that will give us 0.0702 equals KC times 586.013. We'll divide that to the other side. Those guys will cancel, and we will end up with a KC value of 1.20 times 10 to the minus 4, looks like. Do a little scientific notation there. Question on that calculation there. And again, we do see kind of the similar result, although they do not equal each other, the KP and the KC value. They do both tell you kind of the same thing. They're both considered a small value of K, which means when we reach equilibrium, we actually will mainly have reactants and mainly the solid. So not a lot of gas molecules probably being produced in this particular reaction. Any questions on how to calculate KP, KC? Obviously, you need to be able to do that and calculate one from the other, and depending on the information given to you. Any questions on that?
Does it matter whether or not we use the formula and we plug the numbers in right away, or we just solve for like the variable first and then plug the numbers in?
Yeah, it's the same thing. You can do it either way. As long as you can rearrange the equation and solve for KC first, and KC would equal KP divided by RT delta N. So, and then plug in the numbers perfectly fine.
Okay.
Other questions? Okay, so what we're going to talk about next here is the actual value of the equilibrium constant and what happens to it if we sort of change the equation. So when we do see an equilibrium constant, it is specifically for how the equation is written. And there are going to be some problems that involve equilibrium constants that are, I guess, the way you could kind of equate it to is everybody's favorite thing, like Hess's law, if you remember for Chem 50, where you added a bunch of little reactions together to get an overall reaction. And there's a lot of times where you may have to manipulate an equilibrium equation and the K value that's associated with it so that you do get sort of the right K value. So that's where we're going to sort of talk about what you do when you sort of add, you multiply an equation and what happens to the K value. So let's first talk about what happens if we do need to add a couple of different equations together to get an overall reaction. So for example, here we have two equilibrium equations, reactions, A plus B goes to C plus D, C plus D goes to E plus F. We could write an equilibrium expression for both of them. So the one on the left here is for the top, and the one on the right is for the second one. Now, if we add this reaction together, the C's would cancel, the D's would cancel, and this would give us the overall reaction of A plus B goes to E plus F. And if we wrote the equilibrium expression for that guy, it would be E times F divided by A times B. Now, although we added both of these reactions together, what actually happens to the equilibrium constant is you multiply the K values together. When you multiply the K values together, C will cancel, D will cancel, and you will be left with E and F on top and A and B on the bottom. So one very common way our situation that develops is you will sometimes have to add multiple reactions together. And if you're looking for the equilibrium constant for the overall reaction, you essentially just multiply all the K values together. So if there's two reactions, you multiply both K values together to get the overall K value. If there's three reactions, you multiply all three K values together to get the overall reaction. So if you are adding two equations, three equations, however many equations together, and they all come together to form an overall reaction, the overall reaction's K value can be found by multiplying all the individual K values together. So we're not adding the K values, but multiplying the K values. And that's what the little guy is yelling about there. Now, in certain cases, if you're going to add one reaction to another, kind of like what happens in, say, Hess's law, sometimes you may not need it the way it's written. You may need to actually like flip the reaction around or reverse the reaction. And that's a common process that is also done with equilibrium. But there's something different that happens with the equilibrium expression than, say, like delta H when you reverse a reaction. When you reverse a reaction with delta H, you simply just change the sign. And that's not really what happens when you reverse a reaction and you look at the equilibrium constant. So here are two reactions which are essentially reverse of each other. So this is N2O4 goes to 2NO2, has a K value of 4.63 times 10 to the minus 3. That number is specific for this equation, exactly how it's written, what's on the reactant side, what's on the product side, and that K value goes for it. Now, if you go, I don't really need it like this, but I need the reverse of that reaction, that is this guy. And if you just look at what happened to the equilibrium expression, for our first reaction, it was a concentration of NO2 squared divided by N2O4. For the second one, our reactants become our products become our reactants. So we end up with N2O4 and NO2 squared on the bottom. They have basically became inversed of each other. So if you reverse a reaction, you take 1 over the K value for the new reaction. And that's what we see here. This is 1 over the K value. 216 would be the K value for that particular reaction. So a K value that you see is specific for that reaction the way it's written, and also the temperature for it. So if I said the K value is 4.63 times 10 to the minus 3, I am speaking exactly how that reaction on the left is written at that temperature. I am not speaking about the reaction on the right, because the reaction on the right, the K value is actually 216. So it's specific for exactly how it's written. And one very common sort of manipulation that you do with these equations is you need to reverse them. So when you reverse a reaction, you basically take 1 over that reaction, 1 over the K value, I'm sorry, and that will give you the 1 for that. Also, what sometimes happens is, for example, if I had A plus B goes to C plus D, and I write my K value for this, which would be C and D divided by A and B. And sometimes when you're kind of putting equations together, you go, I don't really need one of everybody, but I need two. So sometimes you may have to multiply by a common number. So if I multiply this guy 2A plus 2B, and then just multiply 2 all the way across here, 2C plus 2D, that would give me a K value that is C squared, D squared, A squared, and B squared. So what I did here is I multiplied by 2. What happened to my K value is my K value has now become squared. If I multiplied by 3, my K value would then become cubed. So if you have to multiply an equation by a common number, you take the K value to that common number. So again, like we did here, if we multiplied by 2, we take the K value and we square it. If I multiplied by 3, we take the K value and cube it, and so forth. So that's, again, a very common sort of thing that you have to do is multiply by a common number. Again, maybe you need 2 of something versus 1 of something. The other common thing that you sometimes would do is the opposite of multiplying, which is dividing. So sometimes maybe you're given the one with 2, and you go, I don't really need 2, I need just 1 of everybody, and that would be going this way. If you divided everybody by 2, we would go from this K value to this K value. And when we're doing that and dividing by 2, we would take the square root of K. If we divided by 3, we would take the cube root of K. Divided by 4, you take the 4th root of K. So if you multiply by a common number, you take K to that exponent, a common number. If you divide an equation by a common number, you take the root of the K to that number. So if we divide by 2, square root, divide by 3, cube root, and so forth. And those are the sort of the common manipulations that you sometimes need to do. And this, again, would be a problem where they would give you the overall reaction and go, what is the K value for this reaction based on these 2 individual reactions or 3 individual reactions? And again, you may have to reverse a reaction, which you take 1 over K. You may have to multiply by a common number, which you would then take K to that number. You may have to divide by a common number, which you would take the root of K to that. Again, the idea there is very much like Hess's law, kind of putting everything together so that everything properly cancels out and gives you that overall reaction that you're looking for. Question on that there. Okay, so again, a couple of things about writing the equilibrium constant expressions that we talked about. Typically, when we talk about concentrations, it's molarity. When we talk about pressures, usually atmospheres is the way to go on that. So again, if it is not in atmospheres, you need to take it from like torr or millimeters of mercury to atmospheres. And again, that's 760 to do that, right? Torr, millimeters of mercury is an atmosphere. And usually if you're doing any type of equilibrium problem that involves pressures, if it's not in atmospheres, you usually want to convert it to atmospheres, even if the problem gives it to you something like torr and then ask for the answer in torr. When we do something like ice tables, you got to take it to atmospheres, do the calculation, and then convert it at the end. So we'll see maybe that a little bit later on. As we talked about, no solids or liquids in the equilibrium expression. Again, they really don't participate and are not really actively participating in what's going on. Again, equilibrium constants are just a number, no units associated with them. And as we've been talking about, when you talk about a specific value of K, it is specific for the actual equation, the way it's written, and the temperature for it. And again, temperature being really the only thing that will affect the value of it. And as I said, if you're adding more than one reaction together and you're looking for the K value for that overall reaction, you actually multiply, not add, but again, you multiply the K values together to get the K value for the overall reaction. as well, and a couple of other sort of manipulation things that we talked about here. If you reverse the reaction, you take 1 over the K value. If you have to multiply by a common number, again, you raise the K value to that common number. So again, like we saw there, if we square it, we'll, if we times it by 2, we'll square the K value. Times it by 3, we would cube it. And as we talked about, no units involved there. And a couple other things just to finish up on here for today. The K value has the same value regardless of how much reactants or products you start with. Again, as I was talking about earlier, as long as you keep the temperature the same, you could throw in there different amounts of reactants and products, and every single time when that system reaches equilibrium, that state where the rate of the forward reaction equals the rate of the reverse reaction, you will get that constant proportion of products divided by reactants. So that ratio of products to reactants is always going to be constant, and you'll get a constant value. Again, even if you don't start with the same amounts, it will always end up being ratio-wise the same value and constant. Again, only thing that will actually change the value of K is if you change the temperature. And what that means is the value of K at 70 degrees versus the value of K at 25 degrees. Those two numbers will be different, but if you raise it to 70 degrees and keep it at 70 degrees constant, the K value, no matter what you start with at that point, will remain the same. It would just obviously be different between 70 degrees and 25 degrees Celsius. Any questions on any of that stuff there? Okay, so we will stop here.